Hey guys, let's make a KiCad footprint. So I have to make a footprint for this sensor right here. This is the Bosch BME688. And you can see here that DigiKey does have a full model, which we could come here and download for KiCad with a step file for the 3D file. But let's say we didn't have this. What would we do? So let's make a footprint from scratch. So we'll open the datasheet and we'll still download the 3D model because we'll need the 3D model for our file. So we'll save it in our KiCad libraries and let's begin. So in KiCad, there's two elements to KiCad that you need to be aware of. You have your schematic and then you have your PCB. You first design your circuit in your schematic, and then once your schematic is ready, you update your PCB from the schematic. So you never edit the PCB and then update the schematic later. You make the changes to the schematic and then update the PCB. KiCad does give you the option to update schematic from PCB, but I don't recommend it. I recommend in your workflow, start with your schematic, draw it out, make sure everything's connected properly and everything has the right footprint, and then update your PCB. So because we have these two main components of KiCad, the PCB and the schematic, we have two types of symbols. We have schematic symbols and PCB symbols. Excuse me, PCB footprints, I should say. So where shall we begin? Let's start with the schematic symbol. This one should be pretty easy, but let's take a look here. I have a folder I call installed, starting with a 1, so it appears at the top of the list here. And that's where I put all my custom footprints. So let's create a new symbol, and we will call it BME688 for now. That's what it's called, right? Yes. Okay. And the symbol U is typical for integrated circuits, which this is not exactly an integrated circuit, but close enough. We'll say that its default reference designator is a U. If this was a capacitor, it would be a C. If this was a resistor, it would be an R. Typically, transistors are a Q, and integrated circuits are typically a U. So we'll stick with U here. Now, when you start, you see you have nothing here but the U. That's all you have. And if you come up here to this button here, the symbol properties, it will open this dialog box where you'll have these 5 default values, at least for KiCad 9 and beyond. These 5 are default and you can't delete them. See, I don't typically write much description, but you see if I try and delete it, the first 5 fields are mandatory. So I typically name my footprints first by what it is. So it's an IC, and then by the manufacturer, which was Bosch, and then a brief description. So it was a sensor, and then the part number, BME688. And if you want, you can put the same thing in the keywords. I don't think that it's necessary, but doesn't hurt. So the BME688 is from Bosch Sensortec. So we'll copy Bosch Sensortec and we'll add one field here called manufacturer. And the manufacturer is Bosch Sensortec. And then we'll add another field here, which I call distributor, so that you can keep a link. And usually I use a DigiKey link unless it's something, it's at Mauser, but it's not at DigiKey or something like that. In a rare case, usually most things are at DigiKey, but occasionally it does happen. And we'll put the link to the DigiKey page, which has the BME688. So if ever I need to go back and find it, it's right there. And also the data sheet. So I'll right click on data sheet and I'll copy a clean link. And then I'll put that for the data sheet. And the value is BME688. Value is typically the part number. Okay. Now you want to make sure, at least for me, I make sure these are all centered vertically and horizontally. And I usually only show the reference and the value. I won't actually show manufacturer or distributor or something like that. For a couple of things like capacitors, you'll have a few extra fields here. You'll have one field called capacitance, where you write in your capacitance. You have one field called tolerance. You'll have one field for your temperature coefficient of your capacitor. For ICs like this, these 7 fields are usually enough. I usually leave footprint blank for now. I don't give it a default footprint. I will put the footprint in the schematic when I'm using it, which I'll show you later on. And then I usually don't put a description. So I'm going to leave this like that. And you'll notice, I'll just save it. You'll notice here now in my library, it's called IC Bosch Sensor BME688. That's because that's from the symbol name here. So you can name it what you want. And you'll also notice a bunch of the fields here are grayed out. That one looks like the data sheet. This one is the DigiKey link. This one is the manufacturer. I don't know why KiCad does this. These will not be there when you put them in your schematic. So I don't know why these appear like that in KiCad, but don't worry about them. So I'm going to move these up and to the right for now, and we're going to draw a little rectangle, which is going to represent our sensor. And don't worry about the size or the alignment. You can always fix that later. Pick the rectangle tool, and then it's very easy to adjust. You can click on it, hit delete, and you hit the E button for edit, and it'll bring up the properties. And I always fill with the background body color. And so this is the standard look for all of my schematic parts. It'll have a nice yellow interior. And now we need to add the pins. What are the pins that we're connecting to on this sensor? So we'll go back here to the data sheet and take a look. Where does it give us the pins? I just saw something for pinout here. Where did I see? Pinout, page 51. Perfect. All right, so here we go. Here's our pinout. And if we notice, this sensor is kind of a good example and kind of a bad example, because you can see here the top view where the pads are not visible. It starts on the right and goes down and then crosses over and comes back up to the left. That's the opposite of, 99% of the ICs you're going to work with. When you're looking from the top, most ICs go, when you have only pins on the left and right side, they'll start in the top left and come down and then across and back up the right side. So they'll typically look like this. This you can see here is the bottom view. That's not typical. Typically, it looks like this from a top view. Typically, from a top view, your pin 1 is going to be in the top left. So this one here is a bit of an exception to what we normally see, but it's still perfectly doable, no problem. So our first pin is our ground pin. So we'll add a first pin here by coming over here and clicking draw pins. And our pin name is ground and our pin number is 1. And that's because we see here 1 is ground. And usually I'll put bidirectional for all. It doesn't really matter. You can leave it as inputs. It generates warnings about connecting inputs to inputs if you don't label them right, but you can just ignore those warnings if you're sure of what you're doing. It's not a big deal. And usually this is a bit of a short pin for me, so I'll usually double that and make the pins 5.08 or 200 mils. Now, when I'm doing PCBs, I usually work in millimeters because I am in Canada. However, the grid for schematics, I keep it in imperial, which is very common, a grid of 1.27 millimeters, which is 50 mils. And I just find most footprints, if you download them, they use this grid. They'll use an imperial grid, not a metric grid. So I keep it like that, and that is the default in KiCad. So we have our first pin, and we see in our top view, pin 1 ground is in the top right. And so let's keep going. Pin 2 is CSB. What is CSB? Chip select pin. So this chip works using SPI, the serial peripheral interface, and that involves 4 pins: our data out, our data in, our clock, and our chip select. Chip select lets the chip know that the master controller of the SPI network wants to talk to it. And that's how SPI typically organizes its communications, because all chips receive the data in line and the clock line. So how do they know to ignore it? They ignore it if the chip select pin is not driven low. It's an active low pin. And so, and this chip is actually a little bit different because it can take SPI or I2C. And so in the case of using I2C, this CSB pin becomes our VDD-IO, or it's the same as VDD-IO. Okay. So what we'll do is we'll label it double then. We'll label it CSB slash VDD-IO, just so we don't forget that. And we can just copy and paste this pin and hit our E button to edit. And we'll call it CSB slash VDD-IO. And it is pin number 2. Now, I'll be honest, guys, I don't like to see CSB for chip select. I don't know why they called it that. Let's make this rectangle a bit wider, huh? Maybe that's a bit too wide. But I don't like to see the term CSB. To me, it should look like this. So I'm going to call it that. So you draw a tilde and then open braces, curly braces, and inside anything that you draw, I will write CS, will appear with a bar on top. That is how I like to see chip select noted. And the reason for that is because it's active low. And so by drawing it with the line on top, you remember that this is an active low pin. You keep that in mind. So now pin 3 is SDI for SPI and SDA for I2C. So SDA for I2C means the data line, and I2C also has a clock line. So I2C only has two pins, data and clock, and it uses addressing to specify which chip it wants to talk to, versus SPI, which uses a physical pin, which we call chip select, to select which chip it wants to talk to. So we'll call this one SDI slash SDA, keeping it in sync with our convention that we're writing the SPI nomenclature first, and then the I2C. So we'll call it SDI slash SDA. SDI slash SDA. And we'll name it pin 3. Okay. Now, guys, if you click the M button, you can move it around. And if you click the R button, you can rotate it around. Okay. Very handy keyboard hotkeys to remember. And then our last pin, we have our serial clock, SCK. SCL is the convention for I2C. So we'll call it SCK slash SCL, SCK slash SCL, and pin 4. Done. So we got half of our pins done already, guys. Easy peasy. Okay. Now, pin 5 we see is over on the left side in the top view. So we'll move pin 5 over. That is going to be SDO. And it says, so that's data out. That doesn't exist in I2C. So it says here ground for default address. So I guess maybe it can have more than one I2C address. I'd have to look that up. How does the addressing on this chip for I2C work if you're able to specify multiple addresses for it, which sometimes you are. So we'll call this one SDO. And you can see here, you're going to need to make this a bit wider, but that's fine. No problem. Easy to do. So that's pin 5, and that is SDO. And then I'm going to call it ADDR, address, okay? Because I don't want to put ground on it. It might be a bit confusing. Somebody might ground it by accident. And so it says ground for default address. And maybe there's other options too. I'm going to have to look through the data sheet and figure out how to set non-default address. So we'll leave it like that. And we'll just pull this guy over a little bit. and you'll see the pin will follow him. I don't know why, but on this side, oh, it does work. Never mind. So that's easy. So yeah, let's leave it like that for now, and we can always adjust later. And it looks like we have a little bit too much at the bottom here. So if we want to make it symmetrical, we can move that down. There we go. And is that, oh no, that's not centered for some reason. Who knows why? I don't know why, but we can lift that up, and yeah, these should be centered. 1, 2. Oh, that's why. That's why. Okay, 1, 2. I had them as 3. There we go. So we can move those closer and move this guy up. Give that a bit of space. Move this guy down, and now if I move that, I should be able to center that right in the middle. Boom, perfect. Okay, so this chip, you can see it's a little bit wider than it is long because we're giving lots of room for the text here, but that's fine. That's not a problem at all. All right, pin 6 is VDDIO in all cases, so that's easy. We'll go copy paste, and we'll call this one VDDIO, and we'll call that pin 6. And pin 7, ground, always ground. So again, Control C to copy, Control V to paste. Pin 7, and that was ground. Pin 7, ground, yes. Okay, and we're almost done, guys. We are almost done. Pin 8, VD, pin 8. All done, guys. Now, we'll hit save, and I want you to keep in mind something that is very important. This pin here is called pin 8. And when you make your PCB footprint, the pad for it needs to be number 8. The pin number and the pad number must be the same. That is crucial to understand. That's how KiCad knows to assign which electrical connection to which pad. And you can name this anything you want. You can name it letters, like for a diode, you'll sometimes call it A or K for anode and cathode. You could call it, HJK. It doesn't matter, but it has to be the same on the schematic symbol and on the PCB footprint pad. So something very important to keep in mind. And you'll see that when we go over to do the PCB footprint next. So last thing, we'll take our little U symbol and we'll put it on top, and our BME688 and put it on the bottom. And we're done, guys. We'll save that. And that is our schematic symbol. So we'll leave that for a second, and we will make our corresponding PCB footprint. So we'll open our footprint editor. The first time you open it, it does take a minute as it's loading all of them. And then you'll find as you're working, if you close it and open it again, it will open much faster the second time. Okay, so again, I have my PCB footprints in a folder I call installed, starting with the number 1. So it always appears at the top. And I'll just come here again, right click, and I'll say new footprint. Okay, and it gives me these basics every time. And we can open the footprint properties up here. And typically, I will set the reference to 1 millimeter as a minimum. I'm working on a project right now that is very, very tiny. And so I am setting the reference designators to 0.8 millimeters in that project. But typically, if you're not really constrained for space, you can keep it at 1 millimeter, and then 0.15 millimeters thickness is a thickness for your silk screen text that your PCB fab house should not have a problem achieving. Anything thinner than that, they may complain. And then our value is going to be our part number. So that is the BME688. And just make sure I got that right. And that's it. We don't really need a data sheet or a description for the PCB footprint, but we do want to name it. And I'll show you again my naming convention. I'll say it's an IC first. If it's an IC, it's an integrated circuit, then the manufacturer, then what it is, it's a sensor, and then the part number. So that's typically how I name my my parts. Now, is it a through hole or a surface mount component? It is surface mount, and there are no through holes in the design. Usually you don't check any of these boxes, but occasionally there'd be a special kind of footprint. For example, something that's purely mechanical. like something that's in your design that you need to see it in 3D to make sure when you're laying out your PCB that there's no collisions, that you're not putting something somewhere where it shouldn't be. And in that case, it might be something that is not in the bill of materials. It's not in the bill of materials for the PCB, so you can exclude from bill of materials. It's not going to be something that is placed on the PCB at the time of assembly, so you don't need it in the position files, things like that. For this one, though, this is a totally normal component, so we're just going to leave it, all of these unchecked, and go OK. And we'll hit save. And usually I will delete this guy. You can also, if you want, move him to the front fab layer. You know what? I'll leave it like that for this example. So front fab is something that is invisible. It's not there on the PCB, but it's used by the PCB fabrication house. So you tell them what's the part number here. You can put the reference designator again on the fab layer so that they are able to reference it at the time of making the PCB using the Gerber files. So our reference here, you can change the font if you want. I use Arial a lot, and you can do it for all of them if you want. I typically use Arial. Let's get started on the footprint. Now, one thing to notice, guys, is these guys are not actually printed. These are on the fabrication layer. We have a front fab and a back fab layer, B fab and F fab. I always put things on the F fab because you assume the product will go on the front layer or the top layer. And if you move it to the bottom layer, the KiCad software will automatically move everything that's on the front layer to the bottom layer. So I typically, in making a footprint, I won't put anything on back fab. I'll just put it on front. And if I place the component on the back, then KiCad will do all that work for me, putting the fabrication layer on B fab. Same thing with the copper layer. I'm going to use the front copper layer, not anything on the bottom copper, because if I do place it on the bottom copper layer, KiCad will do all that for me. I don't have to worry about that. So let's get started here. What does our PCB footprint look like? So we see here, zoom in a bit, some package dimensions where we have 2.4 millimeter pitch between pads from left side to right side. And then we have 0.8 millimeter pitch between pads in the same column on the same side. And it's also, so that means it's also 2.4 millimeters from first pad to last pad in the same column. So all of these details are going to be very important for us to make this PCB footprint. And here we see our landing pattern. That is what they call the PCB footprint. And here we have our landing pattern, which they mean the copper, and then our solder stop, sometimes called solder mask. And in KiCad, that is going to be your mask layer, your front mask. But I'm going to show you how to design your pad so that the extra solder mask is done automatically for you, and you don't have to worry. And whenever you move a pad, the solder mask will move with you. So let's make pad number 1 first, and we can see this is the top view. So our pin 1 is in the top right. Again, this is not normal. Normally pin 1 is in the top left, but on this one, it's an exception to the rule, and it's a good example because it's showing us to be careful and how to make this PCB footprint from scratch when we have, exceptions like this. So let's make pad 1, and we can see here from the sizes, the pad should be 0.4 millimeters by 0.4 millimeters, and our solder mask should be 0.6 millimeters by 0.6 millimeters. So that means the extra on each side is 0.1 millimeters. So 0.1 millimeters that way, 0.1 millimeters that way, etc. So let's do that, okay? In our footprint here, we'll come up here and select Add Pad, and we'll put in our pad 1. And we'll start with pad 1, and we'll set up all the parameters for pad 1. And then since all the pads are identical, we'll just copy and paste and change the number. So we'll come in here, we'll click it, and we'll hit the E button for edit. And we'll say, what kind of pad is it? It is a surface mount pad. Do we want a rounded rectangle? No, we just want rectangular because we see here perfectly square. And the size of it is down here. So our size was 0.4 millimeters by 0.4 millimeters. And we want to include our paste layer and our mask layer, our solder mask and our solder paste. So we want to make sure those two are included in, as well as our copper layer, which we have chosen F for the front. As I said, guys, always choose F. And if you need to move it to the back, KiCad will do everything for you. So now that we have that set up, let me show you how to set it so that the solder mask expansion is done automatically and you don't even have to think about it. Overlooking this connections tab here, move over to clearance overrides. And you see here this field here for solder mask expansion. And we will write 0.1 millimeters. And you see automatically this purple now around the pad is added just like that. And you see how small this pad is now. We're dealing with tiny little pads here. So where are we from the center line here? Here's our center line. And we know from here to here is 2.4 millimeters. So the pad is always, the coordinates for the pad are always from the center, okay? So we need the center to be, it doesn't actually show. You can do the math if you want, but we know from up here that they are 2.4 millimeters apart. And that means from the center line, one of them is 1.2 millimeters this way, and one of them is 1.2 millimeters that way. And that is denoted by positive X and a negative X. So for our top right, we should have 1.2 millimeters this way, and then our X direction would also be 1.2 millimeters in the Y direction. So let's try that and see if I didn't make a mistake in my math. So our X should be 1.2 because positive is to the right. And where is our center? Our center is right there, denoted by this tiny little purple cross. And we can move these out of the way for now until we're done. So this guy will say he's 1.2 and 1.2. Okay. Now, if I copy and paste him, and I'll put him directly on, and I'll change his number to 2, and I will move him down by 0.4 millimeters, because remember the pitch? Sorry, excuse me, 0.8 millimeters. 0.8. So one nice thing about KiCad is it can do the math for you. If you know you need to go down by 0.8, you can just go minus 0.8 and hit enter, and it will automatically update it to 0.4 millimeters for you. And keep your X the same, of course, because these are in a vertical line. And so we'll just copy paste that again. This one is number 3, and I'll show you now. This is 1.2x. I moved him over, so we'll change him to 1.2. And then this guy is 0.4. So we'll copy that, put that in here, and then we'll say minus 0.8, and we'll get a negative 0.4 right there. Okay, now are we doing it properly? Yes, we are. You see 1, 2, 3, 4 on the right-hand side. 1, 2, 3, 4 on the right-hand side. So let's do one more, copy paste. We'll change the pad number to 4, and the X doesn't change, but we'll go again minus 0.8, and now those should be lined up. Now, let's make our lives really easy. Let's copy all 4 and paste them on. Okay, now these will have the exact same Y values, but our X value will be negative 1.2 now. So we'll just say negative, boom, all done. Easy, easy. And what's the numbering again? 5, 6, 7, 8 going up. So we'll change this one to 5, this one to 6, this one to 7, and this one to 8. And we're done. Our pads are placed. Now, let's check if they line up by showing you how to add the 3D file. Okay. If we hit Alt-3, we will pull up our PCB design so far. We don't have any 3D part yet, which is important because we need to make sure when we're designing our PCB and putting it into some assembly that there's no collisions with anything. So let's add our 3D file. We will come up here to our footprint properties and click this tab here, 3D models. And now we will open this folder and go to our library, which was called KiCad Libraries. And did we download as a step file? I don't actually remember. Let me go back and check here. What did we download? No, we downloaded a zip file. So let's open it and let's extract all. And let's name the library IC Bosch Sensor to keep it consistent. Actually, I think I already did that. I think I downloaded it once before. Did I not? Didn't I? I think I did. Let me just make sure here. Yes, I did. I have it already. So it's already there. So I downloaded it twice. That's okay. All right. So we have it in a folder called IC Bosch Sensor BME688. If you open this folder, we'll see a step file right here. See it? Looks good to me. Now, oftentimes you'll add it and it will be in the wrong orientation. That's fine. No problem. We have our 3 rotational values here. And usually it just has to be rotated 90 degrees in some way. So we'll start with X, and that looks correct, but it went the wrong way. So I'll go plus 90, and that's sitting nicely now. And then we zoom out a bit with our mouse wheel. We push down on our mouse to move it around. We can see that it's sitting flush with the board. So I don't think we need to offset at all. So you can see even if you did a 0.1 millimeter offset, it's still raised a bit too high. So I think just having it at 0, whoops, my mistake. I think having it at 0 is just fine. And now we can reduce the opacity a little bit to see the pads are lined up with our pads perfectly. Okay. And if we come back to our drawing here, it shows us the package dimensions has a vent hole from the top view, has a vent hole in the bottom left, which we see in our model right here. So I believe we have this properly laid out. Looks like all of the pads have lined up very nicely. And if you want to offset it by a little bit, you can see the pads here on the component versus the pads on the PCB. So everything's looking good. I'll raise that opacity back up so it looks normal. And we can hit OK and move on here. Now, if we hit Alt-3 again, we can see our 3D model is now there. So let's finish up this footprint and we'll be all done. We've got our schematic symbol and we've got our PCB footprint. So let's finish this up. First, we're going to add a bit of silk screen to denote the border of the IC. And how close, if we hit Alt-3, how close is it to the pads? Fairly close. So we'll draw a little bit outside the pads and go from there. So we'll click our draw rectangle and we'll start maybe 1, 2 diagonal, okay? And come down here, 1, 2. So it's nice and symmetrical. And you can see it's symmetrical because the center point is right on the center, our 0, 0, XY value there. So this thickness, 0.1, 0.15 is usually what I like to do. I think 0.1 they can probably achieve at most PCB fab houses. I usually use 0.15, especially for text, just to be sure. But let's check it out. That looks pretty good to me. That's a nice border around. And how do we denote pin 1? Well, there's 2 ways that is typically done. One way is to draw a bar, which is visibly different from the rest of the silk screen around the IC, which denotes pin 1. I'll show that in another video. I don't think this this design is really appropriate for that. So I will show on this one the other way that's very common, which is just to draw a dot. So we'll take our circle diagram here and we'll just draw a small little dot. So we'll say a radius of 0.1. And then in our properties here, we'll say our line width is double our radius. So we'll say line width of 0.2 and that will give us a nice full circle. Okay, and now we place this right near pin 1, just around there is fine. Okay, now when the PCB is going for manufacturing, they will be able to tell instantly where pin 1 is supposed to be located. And one more thing that you can do is Control C, Control V, make a copy of this one and put this one on the front fab layer. So they have a dot denoting it on both the silk screen, which is visible, is printed on the PCB, and on the fab layer. And I usually just offset the front fab dot by 1, so both of them are visible. And now, one more thing we want to add, guys, is a courtyard. A courtyard is used in KiCad to make sure that components are not too close to each other. So we let KiCad know the clearance that we want around. And some components have very big courtyards because they need a lot of clearance. This one, I think, will just make the courtyard the same as the silk screen outline, and that should be more than fine. And my courtyard, because it's not printed, I always keep it 0.05 millimeters thick so that it's distinct and not the same as clicking. So clicking the silk screen can be done fairly easily, and clicking the courtyard can be done fairly easily. And that's it. I'm going to go save here, but you can see we have everything that we need now. We have our 3D model. We have our reference designator, which I will move down now because we are ready to go. And the other thing to keep in mind, guys, is these front fab layers, they're not printed. So you can make them any size that you want. It does not matter. So I will make these 0.25 millimeters because don't forget, in the Gerbers, they can zoom in as close as they want. So we'll move this down, put the reference there, and the BME688 as well. We will say 0.25 width and 0.25 height, and move that down. And I think, guys, we are all set. So we've got our paste layer. If we click paste, we can see the paste on all the pads. If we click our mask, we see our mask, and we've got our copper. That's all we need. We've got our reference designator. We've got some front fab information for them as well, telling them the name of the component, the reference designator, and also the pin 1 indicator on both the silk screen and the front fab. As well, our front courtyard is done. Typically, when I do a footprint, that's all I use. Am I missing anything, guys? You let me know. Do you guys use other things? I'd love to hear about it. Let me know. But we'll stop here for now. And in the next video, we're actually going to make a PCB with this footprint. So thank you guys for watching. I hope you found this educational. Let me know any other components you'd love to see a footprint made for, and I'll try and help you out. Have a great day, guys.